EET 114, Chapter 26, the circuit responds to a non-sinusoidal circuit. So here we have a Fourier series voltage, okay? And it was the same form that basically we were talking about before. So to get the RMS voltage as a function of the voltage sinusoid amplitudes, which would be the V sub m's, okay, in front of the sines and cosines. So you use this formula, V sub 0, which is the DC or average value squared, plus V sub m1 squared plus V sub m2 squared, so on and so forth, to V sub mn squared. Then we have the cosines, if they're even there, the V prime squared m1, and so on and so forth, the V prime squared m2, V prime mn squared. And then you take that entire quantity, divide it by 2, add it to V0 squared, take the square root. Um, Here I have written this is the general sinusoidal equation. You guys remember what this looks like. So these two equations are the same. The only thing they did with this equation is they used the RMS voltage as a function of the voltage phasor magnitudes. This is the general form of the phasor. Okay, I used a bold V, meaning it's a vector, and then this is VRMS, angle of theta. The relationship between VM and VMRMS is VM equals VRMS times the square root of 2. So VRMS would equal VM divided by the square root of 2. Okay, just remember VM is the max, it's the bigger of the two. So this is the relationship. So what they did was they put all the phasor magnitudes in there of this equation, okay? And then you can find the VRMS of the total equation. What is the RMS? It's basically the DC equivalent of this entire equation, okay? Same thing for the current, same exact thing. They just took, in this example, they took the DC value of the current, squared it, plus the amplitudes squared, add them up in the numerator, divide by 2, and then add it to the DC squared, take the square root. And then in this example, they already took the RMS values of the phasors. So it depends on the information that you're given up front. The power is going to be V0 times I0, which is the average value. It would be, this average value of the voltage times the average value of the current, and then so on and so forth. It's V1 I1 cosine of theta 1. Theta 1 is going to be the difference between the two. Uh, you have to look at the ones with the same frequency. Okay, whenever you have an equation like this, then these values, you compare values that have the same frequency, like omega and omega, 2 omega, 2 omega, 3 omega, 3 omega, like that. You can't cross frequencies, okay? We'll see that in an example in a second. So this is the total power delivered, which is also equal to, with the phasor form, it would look like this: I0 squared R plus I1 squared R plus I2 squared R, so on, and up to I sub n squared R. And then the total power is also I RMS, would be this would be the total current RMS value squared times R. So for addition and subtraction of non-sinusoidal waveforms, the Fourier series expression for the waveform resulting from the addition or subtraction of two non-sinusoid waveforms can be found using phasor algebra if the terms have the same frequency are considered separately. So you can only consider two terms that have the same frequency. For example, the sum of the following two non-sinusoidal waveforms is found using this method. So we have V1 and V2. This is the equation for V1, and this is the equation for V2. So the first thing is you combine your DC terms. They call it VT for total voltage, 0, which is the DC component. And then they just took the 30 plus the 60, got 90. Okay. Part 2, omega equals 20. So you look at these two terms here, where omega is 20. And then they have VT1 max equals 30 plus 20 equals 50. They just took the two amplitudes and added them together. So then VT1 equals 50 sine 20t. Okay, so you just basically added these two sinusoids together. For omega equal to 40, this one up here, I don't know why they put those three dots there, but there's nothing there, okay? Usually that means a continuation, but for V2, there's 20 sine 40t, so that's all it is VT. The total voltage is 20 sine 40t, and step 4 is omega equal to 60, which is the last two terms. Now, they put in a little sneaky little trick here. This is a cosine, so you can't just add these two together. You have to convert that cosine to a sine and then add them together. So what they did was they converted this 5 sine 60t plus 30 into its phasor form. So you take the 5 divided by the square root of 2, which is like multiplying 0.707, and then the angle is just 30. So that ends up being 3.54 angle of 30. And then the 10 cosine 60t, convert that into sine by adding 90 to it. So 10 sine 60t plus 90. Then they take the 10, multiply by 0.707, and then the angle is actually 90 degrees. So that equals 7.07 angle of 90, and then you add these two together. Okay, like so. And the way you add them together is you convert them to a rectangular form, like this. This is this first term converted. We went over that. And you convert this term into its rectangular form, which is just J7 times 7.07, and the 3.07, and then you add these two terms together, and then you convert back to polar, and this is your third term. So then you have to convert that back to a sinusoid. You take this, multiply it times the square root of 2 to get 13.24, and then this is the frequency sine 60t plus 70.85. So then the final equation looks like this. Okay, you take your 90, then you take your 50 sine 20t, put it here, 20 sine 40t, put it here, and then this 13.24 sine 60t plus 70.85 degrees. So that's how you add two non-sinusoidal equations together.